So both the effects are present in certain kind of material. Generally, the material which does not have center symmetric, materials which does not have center symmetry, produces piezoelectric effect. In centrosymmetric materials, what happens that the displacement of the charge are symmetric, so therefore the net effect is balanced out. So that's why for non-centrosymmetric materials, both amorphous and crystalline, so piezoelectricity is present. So it is present in both. It is present in both crystalline and non-crystalline materials. In crystalline materials, what happens, because the deformation is through molecular displacement and thereby the disbalance of charge, so therefore the response is very fast, whereas in large polymeric molecules the time response may not be that fast. However, piezoelectricity is also present in large quantity, or the piezoelectric coefficient is quite large in case of polymeric material as well. So generally it is expressed in terms of polarization. It can be expressed in terms of polarization. For dielectric materials, because the charges are available between the two surfaces, there has to be certain kind of dielectric property. It can be harnessed it is found like mainly in dielectric material. Because the displaced charge charges need to be made available across the two surfaces. So it can be related by dielectric polarization and electric dipoles. It can be interpreted in terms of dielectric polarization and dipoles. as D equal to epsilon naught is the permittivity, or epsilon, maybe epsilon. So epsilon E plus P. So that way it can be related. P is the polarization, D is the uh, uh, charge or dielectric flux. P is the polarization. Electric polarization, which is equal to the charge that is bound in the surface. That's why dielectric property is important, which is equal to the bound charge density. So this polarization P could be related to D into sigma, which is known as the direct effect. D is a tensor, okay, depending on the three-dimensional sorry. এই আমি একটা ক্লাসে আছি হ্যাঁ 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 ফোন করছি so P equal to D into E. D is the piezoelectric coefficient tensor, which is simplified as a matrix. And sigma is the stress. If stress is say Newton per meter square, then piezoelectric coefficient would be P would be in picocoulomb or coulomb per Newton.
Excuse me, sir.
P would be in coulomb, and yeah, tell me.
Sir, what was epsilon and E?
Epsilon is the dielectric constant.
Okay. So, and E?
E is the electric field.
Okay, sir. Thank you.
Okay. So basically, due to the application of electric field, there would be some polarization. So that is epsilon E, and the other is the induced polarization P. Okay. So together, the dipole moments will be created. Now, in absence of any electric field, we will have only stress induced effect. Okay. So that's why piezoelectric effect deals with the polarization. So this polarization can be due to the applied electric field in case of piezoelectric material, or it could be induced by mechanical field as well, that is stress. Okay. So there are two contributions to this dielectric, this charge displacement. So in general, if we define the polarization in absence of E, so then it is related to a direct effect, that is through the piezoelectric coefficient D and the sigma. All right. So P is in picocoulomb per meter square, and then D would be in picocoulomb per Newton. So the reverse effect, reverse piezoelectric effect, we will have, oh, again I am using another epsilon. Okay, so this is again strain. Strain E is equal to D into E. Okay, so this is the reverse effect. So here this E is the electric field. And D is the same piezoelectric coefficient. So now there are several other factors as well for piezoelectric effect uh, uh, to be produced. So these are like electromechanical coupling coefficient, then charge coupling coefficient. All those are also necessary to study to make a piezoelectric device. But this is the basic effect.
Hello, sir.
Yes.
Sir, what is the meaning of dielectric flux?
The electric flux is like, say, if the charges are static, then there will be electrostatic for field lines, between positive and negative charge.
Yes,
So
sir.
the number of lines are, if you count, those would be the dielectric flux, or
Okay, sir.
electric flux you can call. And
Okay, sir.
because we are dealing with dielectric material, charges are stationary and bound. So that's why the piezoelectric effect we have defined as the displaced charges bound between the two surfaces. Okay.
Okay, sir. Thank you, sir.
So now we go to the next page. Now the D, as I was talking, that small d, piezoelectric coefficient, in general is direction dependent. Piezoelectric coefficients are direction dependent. So because the stress can be of three direction, okay, so usually D is a tensor. Okay, so D and usually a tensor 3 cross 3 cross 3. However, depending on the general definition of stresses, this tensor is simplified and expressed as matrix, because 3 cross 3 three-dimensional tensor is a little difficult to interpret. So the tensor is usually
So what is a tensor?
a tensor, because if you have a variable which is in 3 dimension and the effect is also in 3 dimension, so therefore for every 3-dimensional effect, 3-dimensional perturbation, the effect will be related by a coefficient. So therefore that will be ijk. Okay. So that means there will be 3 dimensions, ijk. So it's a 3-dimensional element T. But the tensor, that 3-dimensional element is simplified.
Sir,
Yes.
yes, sir. Why do we have a 3 cross 3 cross 3 tensor? Like, sir, the direction of stresses could be like in the direction x, y, y, z, and zx, and totally there would be uh, like there would be, I think, six total directions possible, because 3c2 is 6. So, sir, why 9, why 27 are there?
Now, usually we have like 3 directions, okay, and
Yes,
the
sir. So,
effect is
cardinal
also,
direction, sir.
huh? There will be 3 direction, no? 3-dimensional physical field is there. So we can have 3 dimension if you do not simplify them as some nominal definitions. In general, there will be 3 dimensions, and also polarization field can also be in 3 dimension. Okay.
Okay.
Because across each surface there will be one orientation, so we can have 3 principal directions. There can be many directions, but 3 principal directions will be there. So stress also we can resolve into 3 principal direction. Polarization also we can resolve into 3 principal direction. So now if we want to relate an element, okay, one element, the change of one polarization, okay, to corresponding application of stress, then we need to have ijk, okay.
Yes, sir.
However, because stress definition is simplified, not usually done in 3 dimension, so that's why we will see that usually D comes as a matrix, though uh, uh, in by definition it should be a tensor.
Okay.
Using the tensor is simplified to a matrix using common formalism of stress. As axial stress and shear stress. So XYZ we could define in terms of XYZ, then it would have been a tensor. So instead of that, what happens that it can be simplified as axial stress and shear stress. So that way uh, those tensor is usually represented by a matrix like all 1, 2, 3 reference is as axial stress, and 4, 5, 6 as shear stress. Then the P polarization, induced polarization due to stress, is defined K equal to 1 to 6 dik, where D becomes now a matrix sigma K. So here, of course, we have not, in absence of any electric field, this is true. Okay, so that means that electric field we have assumed as 0. So this is for the direct effect we are talking of. So where if there is some electric field present, then this P will be also contributed by the electric field and the mechanical field together. Okay. So in matrix form, we can have P1, P2, P3, D11, D12, like that up to D16, D21, D22, up to D26, D31, D32, D36, oh, sorry,
Hello, sir.
yes,
So, like, we can generate such a matrix definition for the strain also, no? Like in the reverse effect, sir. Sir, in the reverse effect also, like the D would be a matrix, and
yeah,
just
yeah,
sir,
yes,
if,
yes,
and sir, since the dimensions of strain is like the length of strain would be from 1, 2, 3, 4, 5, 6. So length would be 6. Therefore, I think, sir, here we would take the transpose of this matrix D. So then we can get a 6-dimensional matrix which we can multiply to the E vector. That would be
yeah,
3-dimensional.
yes, for reverse effect also we will get it. For the reverse effect, epsilon 1 to epsilon 6 will be there. Okay.
Yes.
Uh, Correspondingly, we will have
Okay.
reverse, for the reverse effect, we will have
So what
that.
are P1, P2 and P3?
Yes.
So what are P1, P2 and P3?
So those are the piezoelectric coefficients. Okay. So if for sigma 1 applied stress, that is for the one direction axial stress, then correspondingly if the displaced charge polarization is P1 is related via D11. Okay. Similarly, if sigma 2 is there, then P1 is related by D12, like that.
So P1, P2 and P3 are in 3 directions.
Yes, these are the polarizations in the 3 directions. So this is polarization. This is polarization and this is stress. All right. So the reverse effect would be just the reverse. We have epsilon 1, epsilon 2, and epsilon 6. So that is D11, D21, D31, D16, D36 into applied electric field E1, E2, E3. So the mechanical deformation as strain is related to the applied electric field in the reverse effect. Okay. Now, generally, luckily for many materials, most of the D's are 0. Okay, there are only 5, 6 D piezoelectric coefficients of that 6 into 3, 18 elements. Only 5, 6 are considerable value or magnitude. So therefore, there are some principal directions, those are necessary to be identified. That is one of the main thing of designing a piezoelectric or making a piezoelectric sensor or device. So we have to first identify the directions. Like for the direct effect, we have to identify the directions which are the sensitive direction, like say for BZT, or barium titanate, etc. This is one example. P1, P2, P3 would be 0, 0, 0, 0, D150, 0, 3, 0. This is, though this is 2, 4, but because of the symmetry, so this is also equal to D15 magnitude wise. So this is D24, so that is equal to D15. Similarly, because of symmetry, this of the structure of the material D31, the next one D32 is also equal to D31. D33 is different. This is just an example for PZT. So therefore, if we give stress in arbitrary directions, we may not get sufficient electric displacement of charge. So we have to identify the corresponding which stressed or directions the charges will be available along with what surface. Okay. So there the electrodes need to be deposited. So then we will be able to collect the charge. I think those we will discuss further, little bit further. So this is just an introduction of piezoelectric effect. About the device, of course, we shall follow the Bentley, because while designing, there are many other aspects like frequency response and also availability, time constant, etc. So those things are also important for designing the device, not only the physical geometric considerations. So, but geometric consideration is also very important for designing piezoelectric sensors. So for an first class, let us stop here. Okay. So tomorrow again we shall continue our discussion on piezoelectricity, but maybe little bit about piezoelectric effect. We shall more go into the circuit aspects of piezoelectric sensor and devices. Okay. Let me.
Hello, sir.
Yes.
Sir, the directions that we are talking about, are they always I, J, and K?
Yes, physically they are Ij and K, but they are according to the application surface, these cross directions are there. Like stress, you can give like shear, no? So that means you can rotate little bit. So that means it may not be that always we give axial stress. There are three principal direction, X, Y, Z. We can put stress like positive X direction, negative X direction. Okay, that is one principal direction. Or like positive Y minus Y direction. Across them, okay, I can give a principal stress. Again, towards Z also, plus Z minus Z, I can give direction. But those are axial. Okay. Now we can give shear stress. Like we can give stress by twisting a little bit towards XY or towards YX. Similarly, we can do it in the XZ or ZX, YZ or ZY, like that. Okay. So that way we can produce shear stress. So those are identified as sigma 4, sigma 5 and sigma 6. Okay. Am I clear, or otherwise tomorrow again we will discuss a little bit about these orientations?
Sir, I have one more doubt.
Sir,
Yes.
Sir, do we have to memorize the values like which are non-zero in case of BA, TI, O3 and so on?
No. It will be given.
Yes, sir. Okay.
It will be given because I am giving introduction to the know about piezoelectricity.
Yes, sir.
Okay. All
sir,
right.
what is PZT?
Lead zirconium titanate.
Sir, and today lab will be there.
Today's lab, if everybody is here, I think 2 p.m. So we have to decide what to do in the lab. Again, we have to start with piezoelectric. So you have to search for some kind of. Let me stop recording.